In 2025, NASA confirmed something that, on paper, simply shouldn't have been true. Voyager 1, the most distant human-made object in existence, had crossed into interstellar space back in 2012, leaving the protective bubble of our sun's influence behind entirely. Out there, in the space between stars, scientists expected to find a magnetic field pointing in its own direction, shaped by forces that have nothing to do with our sun. Instead, Voyager 1's instruments recorded a magnetic field running parallel to the one still inside our solar system, as though the boundary separating us from the rest of the galaxy wasn't nearly as clean a dividing line as anyone had assumed. For years, this reading sat as an unconfirmed oddity, a single data point that could have been coincidence. Then Voyager 2, its twin, crossed that same boundary years later and measured the exact same thing. NASA's own scientists called it, in their own words, a surprising result. And it's the kind of surprising result that has forced a genuine rethink of what the actual edge of our solar system looks like. To understand why that single finding matters so much, you first have to understand exactly what Voyager 1 is and how it ended up in a position to make this discovery in the first place. Launched on September 5th, 1977, Voyager 1 was originally built to do one specific job: fly past Jupiter and Saturn, take close-up photographs no human instrument had ever captured before, and beam that data home. It did that job spectacularly well, discovering new moons and previously unseen rings around Jupiter in 1979, and returning some of the most breathtaking planetary images of the 20th century. But Voyager 1 kept going, propelled by the same gravitational slingshot maneuvers that had carried it past the outer planets, drifting further and further from the sun long after its original mission had technically ended. By August 25th, 2012, at a distance of roughly 121 astronomical units from the sun, Voyager 1 crossed a boundary called the heliopause, becoming the first human-made object ever to leave the heliosphere, the vast bubble of charged particles and magnetic field lines that our sun blows outward in every direction, and enter true interstellar space. A threshold no spacecraft built by any nation had ever crossed before, and none has crossed since, aside from its own twin years later. As of 2026, the spacecraft sits more than 25.5 billion kilometers from Earth, moving away at roughly 17 kilometers per second. Its radio signal is now taking nearly a full day to reach home. The heliopause itself is worth understanding properly, because it's the actual stage on which this entire story plays out. Think of the heliosphere as a bubble. The sun blows into the surrounding galaxy, made of solar wind, the constant outward stream of charged particles our sun continuously emits in every direction. That bubble doesn't expand forever unopposed. Eventually it runs into the interstellar medium, the thin soup of gas, dust, and charged particles drifting between star systems, itself partly shaped by the winds of neighboring stars. Where these two pressures meet and roughly balance out is the heliopause, a genuinely turbulent, dynamic frontier rather than a simple, clean line on a map, not unlike the way a ship moving through water pushes up a bow wave ahead of its hull. As the entire heliosphere moves through the surrounding interstellar medium, following the sun on its own slow orbit around the center of the galaxy, this pushing motion can even generate something resembling a bow shock out ahead of it, a region of turbulence directly comparable to the wake a boat leaves as it cuts through open water. Scientists had long assumed this boundary would behave in a relatively predictable way, with the sun's magnetic influence essentially switching off once you crossed it, replaced cleanly by whatever magnetic environment the wider galaxy happened to have in that particular patch of space, a tidy, well-defined seam separating everything that belongs to our solar system from everything that belongs to the rest of the galaxy. That's exactly the assumption Voyager 1's magnetic field readings ended up complicating. When Voyager 1's magnetometer recorded field lines just beyond the heliopause running parallel to the field lines still inside the heliosphere, the finding could easily have been dismissed as a fluke, a single spacecraft catching one unusual local reading in one particular direction of the sky. NASA's own scientists were candid about that uncertainty at the time, noting they had only one sample of these exterior magnetic fields and genuinely couldn't say whether the alignment reflected some broader characteristic of the entire boundary region or was simply a coincidence tied to Voyager 1's specific flight path. Basic physics gave scientists good reason to expect otherwise in the first place: the sun's magnetic field and the galaxy's own background. Magnetic field are generated by entirely different processes operating on entirely different scales, one shaped by the churning interior of a single star roughly 4.6 billion years old, the other shaped by galactic. Scale dynamics that have nothing whatsoever to do with our particular solar system. Finding them lined up neatly at the exact point where one supposedly gives way to the other was, by that logic, exactly the kind of coincidence nobody had actually predicted. That's precisely why Voyager 2's confirmation mattered so much. Voyager 2 crossed its own version of the heliopause in a completely different direction of the sky in 2018-6. Years after Voyager 1, and along an entirely separate trajectory, and its own magnetometer turned up the same basic result. The magnetic field just outside the heliosphere lined up with the magnetic field just inside it. Two independent spacecraft, launched decades earlier with 1970s-era technology, crossing into interstellar space along two different paths, both reporting the same unexpected alignment. That's not the kind of pattern easily explained away as instrument error or a one-off local anomaly. It suggests instead that this alignment reflects something genuinely characteristic of the boundary itself, at least across the two specific regions of sky where humanity's only two interstellar spacecraft happen to have crossed it, raising the tantalizing and still unresolved question of whether the same pattern would hold true anywhere else around the heliosphere's entire surface. Information nobody will have any way of directly verifying until some future spacecraft eventually crosses the boundary somewhere else entirely. Alongside that magnetic field puzzle sat an equally strange finding involving temperature, one that eventually earned the nickname the Wall of Fire in press coverage of the discovery, a term worth using carefully since it describes something considerably stranger and considerably less dangerous than the name implies. As Voyager 1 approached and crossed the heliopause, its instruments recorded charged particles reaching temperatures somewhere between 30,000 and 50,000 Kelvin, translating to roughly 54,000 to 90,000 degrees Fahrenheit, genuinely staggering numbers by any ordinary definition of heat. Hot enough to vaporize almost any material we're familiar with under normal atmospheric conditions here on Earth. But this isn't fire in any recognizable sense, and it isn't dangerous to a passing spacecraft, the way you might instinctively assume. The plasma at the heliopause is so incredibly thin, so sparse in terms of actual particle density, that there simply isn't enough physical material present to transfer that extreme thermal energy into anything Voyager 1's hull would actually feel. Temperature, in this context, is really describing how fast individual particles are moving and colliding, not how much heat energy is available to burn or melt something passing through. It's the difference between a sauna, where dense, humid air at a survivable temperature can still make you sweat almost instantly, and the near vacuum of space, where particles can technically register as scorchingly hot while carrying nowhere near enough density to actually cook anything they touch. The same basic principle that lets astronauts survive spacewalks, despite the technical temperature extremes of direct sunlight versus shadow in orbit. What causes that extreme, patchy heating in the first place appears to be a process called magnetic reconnection, where solar and interstellar magnetic field lines snap apart and realign with each other, releasing bursts of energy in the process, not unlike the mechanism behind solar flares back near the sun itself, just playing out at the opposite edge of our entire solar system instead. That process helps explain why the heliopause region doesn't look like a single, uniform layer of extreme heat, but instead a genuinely patchy, uneven mixture of scorching hot pockets sitting right next to comparatively cooler regions, evidence that the boundary is being actively shaped and reshaped by ongoing localized magnetic activity rather than sitting as one static uniform shell around the solar system. Some researchers, studying the readings, have suggested the interstellar magnetic field lines pressing against the heliosphere from outside appear stronger and more tightly organized than earlier models predicted, meaning the boundary itself may be getting squeezed and warped from the outside, not unlike a balloon reacting to uneven pressure applied against its surface, rather than expanding or contracting in the smooth, symmetrical way earlier theoretical models had assumed. Taken together with the magnetic field alignment finding, the picture that emerges is a heliopause considerably more dynamic, more turbulent, and more actively interactive with the surrounding interstellar medium than scientists had modeled before Voyager actually got there to check. That wasn't even the first strange signal Voyager 1 had picked up from this region. And understanding the earlier oddity adds real weight to just how genuinely puzzling this entire stretch of the mission has become. Back in 2020, Voyager 1's magnetometer registered an abrupt jump in the intensity of the magnetic fields embedded in the surrounding interstellar plasma, while its plasma detector simultaneously measured a matching rise in plasma density. Similar transient spikes had actually been observed before that point, and in every previous instance, the readings eventually settled back down to their baseline levels after a period of a few months, consistent with a fairly well-understood explanation. Bursts of solar wind streaming outward from the sun, slamming into the heliopause boundary from the inside, compressing the surrounding interstellar plasma and briefly intensifying its magnetic field in the process, the same way pushing on one end of a spring compresses and briefly stiffens the coils further down its length. Adam Sabo, an astrophysicist at NASA's Goddard Space Flight Center and the principal investigator for Voyager's magnetometer instrument, described the underlying mechanism plainly, comparing the sun's role to a piston repeatedly pushing outward and generating these pressure waves that eventually reach all the way out to where Voyager 1 sits. The anomaly that began in 2020, though, simply didn't behave like its predecessors. Rather than fading back to baseline after a few months the way every earlier spike had, the elevated readings persisted month after month, refusing to settle down the way the established piston and pressure wave model predicted they should. That persistence led some of the mission's own scientists to start questioning whether this particular disturbance had actually originated with the sun at all, raising the genuinely open possibility that something else entirely, some source or process intrinsic to the interstellar medium itself, rather than anything traceable back to solar activity, might be responsible for what Voyager 1 was recording. That's about as close as this entire story gets to a genuine scientific mystery in the fullest sense, an anomaly that broke the pattern of every previous similar event, that didn't resolve the way established theory said it should, and that left working scientists at NASA's own Goddard Space Flight Center openly uncertain about its cause, years after it first appeared and with no clear resolution in sight, even as of the most recent data Voyager 1 has been able to transmit. Layered on top of all of that sits a separate, more technical but equally significant discovery involving something called plasma oscillation events, narrow, faint bursts of plasma wave emission that Voyager 1's plasma wave subsystem has been detecting consistently since 2017. Researchers analyzing this data found that these emissions have persisted continuously enough to give scientists something genuinely unprecedented: a continuously sampled measurement of interstellar plasma density stretching across roughly 10 astronomical units of space, with an average sampling resolution of just 3/100ths of an astronomical unit, a level of fine-grained detail about the density of the material between the stars that had simply never existed before Voyager 1 started picking up this specific, subtle signal. To put that sampling resolution in perspective, it means Voyager 1's instruments have effectively been taking a density reading of interstellar space roughly every few million kilometers of travel, an extraordinarily fine-grained data set for a region of the universe that, until the spacecraft arrived, had never been sampled directly at all, only inferred indirectly from telescopes observing light, passing through the interstellar medium from enormous distances away. Those measurements revealed genuine density fluctuations at the scale of individual astronomical units, effectively mapping out turbulence in the interstellar medium itself in between the larger, more dramatic plasma oscillation events that had first drawn attention to this region. Scientists studying the phenomenon aren't entirely certain what generates these narrowband emissions, pointing to possibilities, including thermally excited plasma oscillations, or a phenomenon known as quasi-thermal noise. But its sheer persistence suggests Voyager 1 may be able to keep tracking interstellar plasma density this way, even during the quieter stretches between the more dramatic, shock-generated events that first caught researchers' attention. None of this scientific richness has come easily, and Voyager 1's ability to keep delivering these kinds of genuinely surprising results has depended on the spacecraft surviving a string of very real, very close calls that had nothing to do with the mysteries of interstellar space and everything to do with the brutal reality of operating 50-year-old hardware across billions of kilometers. In November 2023, a corrupted computer chip rendered Voyager 1's transmissions completely unintelligible, cutting off meaningful communication with the spacecraft entirely. Engineers back on Earth spent months painstakingly working through the problem across a communication delay stretching over 22 hours each way, effectively meaning that every single diagnostic command sent to the spacecraft and every response confirming whether it had worked consumed nearly 2 full days round trip before engineers could even learn whether their latest attempted fix had made things better or worse. Eventually, they managed to nurse the spacecraft back to functional health, identifying the specific corrupted section of memory and finding a workaround that let the onboard computer route around the damaged portion entirely. Voyager 1 resumed transmitting engineering data first, and then in May 2024, finally resumed genuine science communications from 2 of its 4 remaining working instruments, ending a communications blackout that had stretched roughly 6 months and had, for a genuinely tense stretch, raised real doubt among the mission team about whether contact with the spacecraft could ever be restored at all. Even with communications restored, Voyager 1's problems didn't end there. Its thrusters, the small components responsible for keeping its high-gain antenna precisely pointed back toward Earth, have shown a persistent tendency to clog, a genuinely serious problem given that even a small pointing error at this distance could mean the difference between a readable signal and permanent silence, since the antenna has to remain aimed with remarkable precision across billions of kilometers for any signal to register back on Earth at all. By April 2026, NASA engineers had turned to an even more drastic set of measures to keep both Voyager spacecraft alive and communicating as their shared plutonium power sources continue their slow, inevitable decline. The team began shutting off individual scientific instruments one at a time, a maneuver NASA's own team informally nicknamed the Big Bang Fix, specifically to free up enough electrical power to keep the spacecraft's most essential systems running for as long as possible. Susie Dodd, Voyager's project manager at NASA's Jet Propulsion Laboratory, has been candid about just how narrow the margins have become, noting that before the mission's 50th anniversary in 2027, both spacecraft will almost certainly need to have additional instruments and systems switched off entirely, with the team hoping at minimum to preserve the cosmic ray subsystem on Voyager 2, alongside the magnetometer and plasma wave subsystems on both craft, the exact instruments responsible for every discovery described here, effectively keeping both spacecraft alive as bare-bones interstellar weather stations, even after most of their other scientific capabilities have been permanently switched off to conserve what little power remains. Despite all of that accumulated wear, Voyager 1 is still headed toward one more genuinely remarkable milestone before its power finally runs out entirely. NASA has calculated that on November 18, 2026, at 2:16:07 a.m. Pacific Time, Voyager 1 will become the first human-made object to reach a full light day from Earth, a distance of roughly 16 billion miles, meaning any single radio command sent from Earth will take a full 24 hours just to arrive, with any reply the spacecraft manages to send back requiring another full day to make the return trip. That milestone is easy to misunderstand, and it is worth being precise about what it actually represents. Voyager 1 isn't leaving the solar system in any clean, final sense by crossing this particular mark, since the sun's gravitational influence, as opposed to its magnetic and particle influence, extends vastly further outward than even this distance, stretching potentially trillions of miles further toward the theoretical Oort cloud. The one light day threshold is a communications milestone rather than a boundary of any physical significance, a number that exists purely because of how light and radio waves travel. But it still captures, in a single figure, just how far this 50-year-old machine has actually traveled, and just how strange it is that engineers on Earth are still successfully commanding a computer built with 1970s-era technology across a communication gap that stretches nearly 2 full days round trip. So was any of this genuinely an impossible encounter in the sense the phrase usually implies? Not in the way that phrase might suggest to someone expecting first contact with something recognizably alien, a physical object, or an intelligent signal. Nothing here involves another spacecraft, another civilization, or anything resembling the dramatic first contact scenario the word encounter tends to conjure up in popular imagination. What Voyager 1 actually encountered was something arguably more valuable to science than any single dramatic discovery could have been: solid, repeatedly confirmed evidence that the boundary of our own solar system doesn't behave the way decades of theoretical modeling had predicted it would. A magnetic field that should have pointed somewhere else entirely lines up instead with the field inside our own solar bubble. A supposedly cold, quiet edge of interstellar space turns out to reach tens of thousands of degrees in patches, shaped by magnetic reconnection events more commonly associated with solar flares, and a disturbance that should have faded within months, the way every earlier version of the same phenomenon had, simply refused to go away, leaving working NASA scientists genuinely uncertain whether it originated from our own sun at all. Voyager 1's power supply is expected to fail sometime around 2026, closing out a mission that has already run for nearly 50 years, longer than anyone involved in its original launch could reasonably have hoped for. Before that happens, NASA scientists are continuing to comb through every remaining scrap of data the aging spacecraft can still transmit, aware that whatever readings it manages to send home in these final months may be the last direct measurements humanity gets from this particular stretch of interstellar space for decades, until whatever future mission eventually follows in Voyager's path finally arrives to check these same readings for itself. There is already discussion within the scientific community about what a dedicated interstellar probe, purpose-built rather than repurposed from a planetary flyby mission the way Voyager was, might eventually look like. And every anomaly Voyager 1 has managed to record in its final years will almost certainly help shape exactly what instruments that future spacecraft carries and what questions it's specifically designed to answer. A spacecraft designed in the 1970s, launched to photograph 2 planets, ended up rewriting basic assumptions about the true edge of our solar system, using instruments that consume less electricity than a household light bulb, transmitting across a gap so vast that hearing back from it now takes the better part of an entire day. That's not an impossible encounter with anything from beyond the stars. It's something almost stranger. Proof that the edge of our own solar system, the literal boundary of everything the sun's influence has ever touched, still had genuine surprises left to reveal, nearly half a century after we first sent something out to go looking, and that the small aging machine responsible for those surprises is still, even now, quietly working to send home whatever it can before its own long, remarkable journey finally comes to an end.